This flight appeared completely normal until something unexpected happened. Well, not a specific flight, but the entire trajectory of commercial aviation. For decades, commercial flight appeared completely normal. We perfected the traditional tube and wing aircraft, pushing it faster, higher, and further. But then, something unusual happened. Commercial aviation began rapidly hurtling toward an invisible, physical wall. We are reaching the absolute aerodynamic and thermodynamic limits of standard aircraft design, right at the exact moment the world is demanding radical leaps in efficiency. So what happens when aviation hits that wall? The upcoming 2050 environmental sustainability mandates are looming over the industry, creating what feels like an impossible crisis for standard airframes. You can only tweak a traditional jet engine so much before physics simply steps in and says no more. A massive disruption isn't just desired anymore, it is literally required. And the search for that disruption has led investigators and engineers down a fascinating, highly classified path. Welcome back to Airflight Space, where we explore aviation events, air safety investigations, industry developments, and the stories shaping our skies. Today, we're taking a closer look at a story attracting major attention in aviation. We are investigating a newly uncovered design that challenges everything we thought we knew about the future of commercial flight. To understand the sheer magnitude of this, we first have to look at where the data actually came from. NASA recently launched the Advanced Aircraft Concepts for Environmental Sustainability 2050 program. They call it ACES. They commissioned the absolute giants of aerospace, Boeing's Aurora Flight Sciences, blended wing developer Jet Zero, and engine titan Pratt & Whitney. The objective? Study advanced technologies that could save commercial aviation from its impending bottleneck. At first, everything seemed completely normal. The heavyweights submitted their highly advanced, expected concepts. But then, an anomaly appeared in the data. A company named Electra quietly submitted an immense, highly detailed proposal. Now, why is that strange? Because Electra is primarily known in the industry for the EL-9, a small, 9-seat hybrid electric aircraft meant for short hops. Yet, out of nowhere, they submitted a sprawling conceptual design for a commercial airliner, capable of carrying over 100 passengers. When we compare their submission to traditional aircraft, the contrast is staggering. A traditional airframe relies entirely on the wings, for lift, right? With a simple cylindrical tube just kind of dragging behind them. Electra's concept completely abandons this for what is known as a double-bubble fuselage. Keep watching, because the deeper we go into this airframe schematics, the more radical it becomes. Just look at the architecture of the double bubble. This isn't just some sleek aesthetic choice. The fuselage itself is precisely shaped to generate lift, actually sharing the aerodynamic load with the wings. And because of this unique, flattened shape, the interior cabin is exceptionally wide, literally wide enough to easily accommodate 2 full cabin aisles in a 100-seat aircraft. It fundamentally rewrites the geometry of regional air travel. But what researchers proposed next shocked the industry. You've got this colossal lifting body aircraft designed for the year 2050. Obviously, it needs to be electric or hybrid to meet those extreme efficiency mandates. But how do you power a 100-plus passenger electric aircraft without spending trillions of dollars rebuilding the entire global airport charging infrastructure? The answer lies in a highly advanced turbo-electric propulsion breakthrough. Here is exactly how the system breaks down. Step 1. 2 underwing turbofans burn standard aviation fuel. But instead of just providing raw thrust, they act like giant flying generators, producing enormous amounts of electricity. Step 2, that onboard electricity is then routed to power 3 separate, fully electric fans mounted way back on the rear of the aircraft. And this detail changes everything. By generating the required electricity mid-flight, using standard aviation fuel, this groundbreaking electric concept requires absolutely zero new airport charging infrastructure. There's no need for giant battery depots at the terminal. It doesn't need completely new power grids. It operates entirely off the existing fueling systems we already use today. Wait, looking closer at the propulsion system, there is a hidden mechanic here that changes everything we know about aerodynamic drag. It relies on a complex technique known as boundary layer ingestion, or BLI. You see, in a normal aircraft, the air scraping along the surface of the fuselage slows down, creating this huge wake of drag behind the plane, essentially pulling the aircraft backward. But by strategically mounting those 3 electric fans right on top of the aft fuselage, Electra's design intentionally swallows that sluggish, drag-inducing boundary layer air. The fans ingest that slower-moving air and violently re-energize it, shooting it out the back. It effectively deletes the aerodynamic wake of the fuselage. It's an absolute engineering masterstroke that tricks the air into acting like the plane isn't even there.
The brilliant mind behind this data is Alejandra Uranga, Electra's chief engineer of research and future concepts. During her time at MIT, she actually helped lead the initial NASA-sponsored research into the double bubble concept. As she states perfectly, what is different now is the ability to use electrification and distributed propulsion to more deeply integrate those systems. Designing the aircraft as a whole system is essential to realizing the full potential of future commercial aircraft.
So, when you combine a lifting fuselage, turbo-electric generation, and boundary layer ingestion, what is the final verdict? Well, when the supercomputers finished crunching the numbers for this NASA program, the final efficiency gain wasn't just some marginal bump. It was a staggering 17%. But you really need to understand the context of this number. This is a 17% efficiency improvement beyond the gains already expected by 2050. By 2050, we already expect highly advanced structures, next-generation engine technologies, and incredibly sleek aerodynamics. Electra's concept takes all of those futuristic best-case scenario improvements and then casually adds another 17% efficiency right on top of them. It completely shatters that physical wall. But the situation was far from over, and it raises a pretty critical question. Is this just paper vaporware? You know, a beautiful digital rendering destined to just sit in a NASA archive collecting dust? Electra themselves haven't actually committed to bringing this exact 100-seat aircraft to market. Their immediate focus remains heavily on certificating their 9-seat EL9 hybrid before the end of the decade. However, what happened next during our investigation truly shocked us. When you look at the syndicate of partners Electra quietly assembled to develop this concept, it becomes crystal clear that this is no mere academic exercise. They partnered with Lockheed Martin's legendary Skunk Works. They brought in American Airlines, Honeywell Aerospace, Hynetics, MIT, the University of Michigan, and UC Irvine. You absolutely don't assemble the greatest minds in aerospace and commercial aviation just to draw a pretty picture. Parker Vasic, Electra's director of product strategy, grounds this entire investigation with a stark dose of reality. He noted that they can radically improve how the airframe and propulsion system work together, all while keeping the aircraft firmly grounded in real-world operations. His quote says it all. The goal is not just efficiency on paper, but concepts that we can actually build, certify, and use. And that real-world integration is the final, most crucial piece of the puzzle. This turbo-electric beast, with its wide double-bubble fuselage and boundary layer ingesting fans, is meticulously designed to fit flawlessly within existing airport infrastructure. It can taxi right up to standard gates, it burns standard aviation fuel, it operates completely within the constraints of the world we have today, while delivering the performance we so desperately need for tomorrow. So, what can we actually learn from this story? What does this deep dive into NASA's ACES program and Electra's bold submission reveal about our path forward? It reveals that the era of isolated upgrades is officially over. We can no longer just bolt a slightly more efficient engine onto a 60-year-old tube and wing design and expect to save the planet. The future of our skies relies entirely on whole system synergy, the radical, seamless merging of airframe design, electrified propulsion, and aerodynamic manipulation. This concept proves that the physical wall blocking aviation's future isn't insurmountable. We just have to completely change the shape of the vehicle trying to break through it. Thanks for watching Air Flight Space. If you found this video informative, leave a like, subscribe for more aviation investigations and stories, share your thoughts below. I regularly read and interact with the community. See you in the next video.